set temperature to, let's say, 40 degrees, 25 degrees, or whatever temperature, there is a PID loop. So there is a PID loop with cycle 3 and with cycle 7. This you can do with each of the cells. There are 5 cells present. Now, how this can work? So this is a water tank. We put in distilled water inside this tank, and the quality of distilled water should follow ASTM 2 standard. So ASTM 2 standard states that your water conductivity should be less than 1 microsiemens per centimeter. So for that we have given a handheld device through which you can measure the water conductivity. And there is a distillation setup. So you can use tap water with the distillation setup, and you will get the distilled water at 4 microsiemens per centimeter. You can use that also. Otherwise, you can do double distillation to achieve ASTM 2 standards.
Double distillation we have to do, right?
So we have to do, yes. So it depends on what kind of water you are filling this distiller with. If you are filling with RO water, you may get that ASTM 2 standard in one distillation also. If you are filling with tap water, it may take time. We take double distillation. So with this water tank, we are supplying to this pump. This is the diaphragm pump. After this diaphragm pump, the water is going to water filtration resin. Why there is a water filtration resin? Because water is circulating inside the cell and coming back again into the water tank. So we want to maintain that water standard. That's why there is a water filtration resin. This is ion exchange resin. From this resin, the water is going towards this manifold. So this manifold is supplying water to each of the cells individually. If we do not want to supply water to any of the cells, we can shut the water. We can cut the water supply through these walls. When these walls are in parallel, it means they are on. When you do it anti-parallel, it means they are switched off. Okay. From each cell, we can see this is the anode, positive side. This is the cathode, negative side. So at anode, your oxidation happens, and water plus oxygen comes from this side. And at cathode, reduction happens, and your hydrogen and water vapor come from this side. So we are collecting oxygen from each of these cells, and this is going to an oxygen manifold. So this is the oxygen manifold line. Through this oxygen manifold line, water plus oxygen is going inside this tank. So due to gravity, water settles down and oxygen is vented out from this pipe. If we want to collect oxygen, we can connect this pipe to this manifold and cylinder stuff, and we can store oxygen. Right? Similarly for hydrogen, we are collecting hydrogen with these hydrogen manifold, these white ones. This is going to a gas water separator. So again, due to gravity, water settles down and it drains out from the system, and your gas is collected here. So the gas will still have some moisture. It will go through a desiccator tube. So in this desiccator tube, we have silica gel, which is a color changing gel, and it will remove most of the moisture from the hydrogen. Now my dried hydrogen is going inside this flow meter, mass flow controller, so that we can see what is the output flow of hydrogen. From the output side, this is going towards a solenoid valve, and the output of solenoid valve is again connected to the cylinder where manifold. So hydrogen is coming from here to this point, then this point, then cylinder. Also in this manifold, we have given a release valve, and this is regulated. So let's say, for example, we have stored some 2 bar of hydrogen, and we can regulate this valve at 0.5 bar. We can connect a fuel cell to this tube, and we can operate our fuel cell at 0. So this is full. This is how it works. One more feature here is, so this is a single cell. When these are connected in series, it creates a stack. So this is a 5-cell stack. If you want to connect 5, you can connect 5. If you want to connect 4, 3, 2, 1, as per the configuration, you can do that. So let's say if I want to remove this cell from this stack, then I have to remove the wiring. I'll connect the wiring. 4 will be in series. I will switch off this valve, I'll switch off this valve, and I'll switch off this valve. So with each cell, 3 valves are connected. Every valve is marked with the number of cells. So we can do our experiments with 1, 2, 3, 4, 5, 6. Alright, when we switch it on, there will be a slight leak. Now, why there is so there are 2 hydrogen lead detectors. One is placed over the manifold and one is placed over here. So safety is very important when we are dealing with hydrogen. Generally, the dangerous level of hydrogen is 1% hydrogen in the air, which is 10,000 ppm, and the lower explosive level of hydrogen is 4% hydrogen in the air, which is 40,000 ppm. But here, because we are dealing with college students, we are shutting this entire system down at 20 ppm. So if even 20 ppm of leakage is detected, this whole system will shut down automatically through release. And when hydrogen vents out and the levels are below 20 ppm, we can restart the system. So this security feature we have implemented here. So relay energization takes time. That's why there is a delay in switching. So this is only for demonstrative purpose because we should not compress oxygen much. And while we are generating hydrogen at 2 bar, there will be pressurization but not much. So if we are doing research experiments, this is not for a demonstration piece and we are doing research experiments, we should keep it disconnected. Oxygen is melting out in the air. And suppose if fifth cell or fourth cell we have not connected, then we can shut these down also anyway. Now my 5 cells are connected. 2.2 is the higher voltage range. So I have set my voltage at 11 volt and at maximum 25 ampere. Then I switch on the output. It will start. Now you can see the hydrogen flowing from this. This is water plus oxygen product. And going back to the tank. To use hydrogen at atmospheric pressure, you can just disconnect from this selector